All right, we're back again. And I'd like to finish the section on workup with looking at a work problem involving fluid dynamics, meaning we're going to calculate the amount of work required to move a fluid. We're going to move a fluid from one place to another. All right, and our problems that we're going to be looking at, we're going to be looking at tanks. So you could think in terms of aquariums, or you could think in terms of gas tanks, or you could think in terms of any kind of container that might contain a fluid at home or at work. And we're going to empty it by considering moving all of the liquid to the top of the container and then letting it drip over the edge. So as an example, if we had some sort of pump, all right, and I have no idea how to draw a pump, but let's just draw kind of a box shape. So just kind of a box shape. I don't know what a pump exactly looks like for something like this, but if we had a pump and it was floating on the top of the water, and what we were trying to do is we're just trying to get the water to the edge so it could drain out. Now, of course, what happens is as we pump water out, the pump falls with the level of the liquid. So now the level of the liquid might be something like this, and the idea is now we have to pump the water up to a higher level before it can fall over the edge, and continuing that idea all the way down. Now the pump is here, and now again we've got to move it further. Think in terms of work, force over distance. So the distance is increasing until we're just sucking up all of the liquid from the very bottom of the tank, and now at that point we're having to move it a much greater distance. Okay, so what we're going to do is we're going to find how much work is required to remove the topmost layer of liquid, then the next layer and 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 the next layer. And we're just going to add up all of those work values for every single layer of water until the tank is empty. All right? And so, of course, when we add up layer after layer after layer after layer after layer, we make the layers infinitely skinny. So we're going to be moving an infinite number of layers, and therefore to calculate the work done, we're going to integrate. All right? And what we're going to be integrating is from A to B. A is going to be the lowest level. Pardon me. B is going to be the highest level for the liquid. And then what we're actually going to be integrating is three things. We're going to be integrating what's called the weight density of the fluid. So whether it's water, gasoline, fuel oil, whatever, maple syrup, whatever kind of liquid would you like to think in terms of, every liquid is going to have its own weight density. Okay? Then the next factor that we're going to be integrating is the volume of every layer. And then finally, the last thing we're going to be integrating is the distance that every layer has to travel to exit the tank. So the cylindrical tank that I've tried to draw over to the left, what would be the distance? Every single one of those layers that we're picking up, sucking up into our pump and putting over the edge, what would that distance have to be? Okay? So we're going to be integrating three factors. Weight density, which is going to be a numerical value. It's not a scalar because it's going to have labels attached, but it is just simply going to be a number, so no big deal there. And then volume, and depending on the problem, sometimes this is just a plain old number, other times it's going to have variables involved. And then for sure, the distance is going to have variables involved because the distances change as we evacuate liquid from any tank. Okay, so feel free to pause the video to make sure you get that basic, I don't know if you'd call it a formula, but at least the basic idea down for calculating work. Okay, so feel free to pause the video. Otherwise, I'm going to move on to the first example. Okay, so first example, I'm going to draw you a tank. And my tank is going to be rectangular, but it's going to be very large. And it's going to be very large because I'm going to choose to use meters. All right, so I tried to draw a rectangular tank. I know this one end looks wobbly. Pretend it's a rectangular prism though. And the dimensions for the tank are 5 meters tall, 3 meters in width, 12 meters in length. Okay? And the tank is filled with a liquid 4 meters deep. All right, so I'll try to make that look somewhat three-dimensional, so you can kind of, the blue is meant to be the liquid. And by the way, and this liquid that I'm going to try to use on this first one is going to be water. And the weight density of water is 9,810 newtons per cubic meter. Newtons per cubic meter. Okay? Now, the idea is we're going to place a pump in the tank, and we're going to start to drain it. Right? We're going to place a pump in the tank, and we're going to start to drain it. Now, to start every one of our problems, you're going to have to establish an XY coordinate system. An XY coordinate system somewhere on the picture. It's going to sound kind of funny because we have a three-dimensional aquarium, but we're going to attach a two-dimensional coordinate system to it. Okay, and I'll explain how we do that as we go along. Usually, the vast majority of the problems, we end up attaching the XY coordinate system to the end of the tank. So I'm going to choose to put my x-axis through the bottom of the tank, and I'm going to choose to put my y-axis up through the left side of the end. So in red, I've tried to draw in the XY coordinate system. Now the reason we need that is when we develop our work integral, we have to have an XY coordinate system so we can pick values and also eventually look at equations for the different dimensions of the problem that we're going to need. Okay? So the way I've set this up, at what value on the y-axis is the bottom of the tank? Well, that would be located at y equals 0. Where's the topmost layer, not of the tank, but where's the top layer of water? Where's the highest level of water? And that would be 4 meters up from the bottom, or on the y-axis at y equals 4. Now the three things we're supposed to integrate are the weight density of the liquid, which is 9,810 newtons per cubic meter, the volume of every layer, so this is the weight density. This, in fact, let me put this a little bit higher. This is going to be the volume of every layer. And since our layers are going to be kind of like sheets, think in terms of our shells problems, we're going to have length times width times height. And question, for every layer of water, the length doesn't change. The length is always 12. When you go from the bottommost layer to the topmost layer, does the width change? The width at the bottom, the width somewhere in the middle, or the width of the top? Do the widths change anywhere on the tank? And the answer in this case is no, so we just get to use 3. And then the height of any one layer, and let me just choose a layer just kind of arbitrarily in the middle of the tank. So if you consider that layer of water, what we're going to do is we're going to think of its height as being infinitely skinny, but it's infinitely skinny in the vertical direction, so that then becomes our differential dy, because it's infinitely skinny in the vertical direction. And if you think about what's true about any kind of liquid, gravity is going to affect it, so our layers have to be always in terms of y, because gravity is going to, every time we remove some water, Gravity's going to level out the liquid, level out the liquid, level out the liquid. So we're always going to be doing things in terms of y. And finally, the distance that every layer has to travel in general is usually the top of the tank minus whatever y value we're talking about. And please notice the top of our tank, not 4, that's where the liquid is, but the top of the tank is 5 meters up on the y-axis. Okay, and that would then be our complete setup for the work done in in emptying this tank with a pump. Okay? Alrighty. Now, if you want to, you can skip over the calculation. I'm going to go through all of the work of the calculation. Feel free to skip this part if you think it's going to be an awful easy one, but if you prefer, go ahead and do that. I'll finish off the rest of it, though, just so you guys can get a numerical answer. When I take out the constants and multiply them together, let me choose a highlighter tool here. The 9,810 is a constant, the 12 is a constant, and the 3 is a constant. Notice all the multiplication signs. So we can factor all 3 of those numbers out and multiply them together. We cannot factor out the 5 because of the subtraction. So, all right, so we factor out the 3. Oops, sorry about that. Forgot to hit my pencil. So we can factor out the 3 constants, and what we're left with is 5 minus y and dy. So, of course, the integral, awful easy to work. What the heck happened there? There we go. So the integration, no worries, attach the variable and add 1 and divide by the new. Then fundamental theorem. Everywhere you see a y, put in 4, so 5 times 4 is 20. 4 squared divided by 2 is 8. 5 times 0 is 0. 0 squared divided by 2 is 0. Okay, 20 minus 8, of course, is 12. And so we end up with 353,160 times 12. And the result then, 4,237,920 joules of work. Remember, this is a work problem. 4,237,920 joules of work to completely empty the tank. Okay? Again, feel free to pause. I'm going to shrink this down so you can see the whole thing. So feel free to check any part of that out, talk it over with someone else. All right? Otherwise, I'm just going to keep on moving. Like I said, if you want to pause and talk this over with someone, that's great. Otherwise, I'm just going to keep on moving and do a second example for this video. And the second example is going to be a bit more difficult because, well, let me draw it out first. Oop, no, that you would be able to see. I think it should be, yeah, that looks okay, I guess. And the labels this time, my tank is going to be 8 feet tall, 6 feet across the top, 10 feet on this kind of that angled side, and then 25 feet in length. And then we're going to fill this thing. I think I'll go with water again. So I'm going to fill this so that it's 6 feet deep. So it's not filled to the tippy top. It's filled to the 6 foot mark. Okay, so the blue is meant to be the water. And when we're in the US system, water has a weight density of 62.4 pounds per cubic foot. So that'll be our weight density value. Okay, like I've said, we have to start every single problem with an XY coordinate system. And you have 2 perfectly fine places to put an XY coordinate system, but I'm going to choose to put the x-axis through the very bottom of the tank, and I'm going to put the y-axis through the left side of the end of the tank. Okay, you can feel free. I think the other obvious place would be to put the x-axis through the top of the tank, and that's totally fine as well. That's totally fine. Okay, then we're going to set up the integral, which is going to give us the work done in placing a pump in the tank and draining it completely dry. Okay, so we're going to be integrating, and what we integrate is from the bottom level of liquid to the top level of liquid, not to the top of the tank, but from the bottom of the liquid to the top. And since the liquid is 6 feet deep, we're going to be integrating from 0 to 6. Then what we're going to be integrating is the weight density of the liquid, again, just a given value, 62.4 pounds per cubic foot. Then we have the volume of every layer, and once again, I'm going to move that up a little higher so that I can kind of spread out the length, the width, and the height. Okay? Now the length of the tank remains the same no matter which layer you're talking about, the very bottom layer, something in the middle, or at the tippy top. The length of the layers are 25 feet. The width, though, is going to change. If I switch to yellow here, the widths of the layers at the very bottom, very narrow, then they get wider, 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 all the way up to the top. And since those change, we need something in terms of an equation or function that's going to give us those changing widths. Please notice all of those yellow widths that I just put into the picture are horizontal. And if all of those are horizontal, of course, what we need is something that says x equals. Okay, so do we know a way to calculate, to figure out a way to find the distance from the y-axis over to that side of the tank? And the answer is going to be yes. I just need to scooch over my picture a little bit. And what I need to do is think about extending the side of that tank up and down. And of course, the shape we just created was a straight line. So what we're going to do is find the equation of that straight line. So that's good old y equals mx plus b time. All right, and please notice the way we set up our xy axis. This line goes through the origin, so the b value is 0. And then the slope is going to be rise over run. So using the height of the tank and the width at the top, the height is 8, the width is 6, so we'd have a slope of 8 over 6. Okay? Now, of course, that reduces. We can cancel a 2 top and bottom. But we don't want to leave it as y equals 4/3 x because all of those yellow widths are horizontal. And when something is horizontal, it has to read as x equals. Therefore, multiply both sides by 3/4, and x is going to be equal to 3/4 y. All right? And if you now try it with any y value along the way from y equals 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8, now that's going to give you the width of any one of those layers. So I'm just going to say it out loud a couple times so I can remember it, and then I'll move it across to my integral. X equals 3/4 y, x equals 3/4 y. So I'm going to put that in now. So the width is going to be 3/4 y. And because of gravity, the layers of water are going to be infinitely skinny up and down. Therefore, our height is going to be the differential dy. And finally, the last thing that we integrate is the distance that every one of those layers has to travel to exit the tank. So the minimum distance that every layer then has to travel is to get out of the tank, it's got to get up to 8 feet. It's got to get to the 8-foot mark. So it's the top of the tank minus the value of y. Okay? And there's the complete setup in calculating work. All right, so just kind of let you take a look at that. All right, and now I'm going to actually go through the rest of it, the rest of the problem. And I'm going to start by showing you the factors that we can take out front. Anywhere we have multiplication, we can factor those numbers out. So the 62.4, the 25, and the 3/4, since we have multiplication everywhere, can be multiplied together and removed factored out front. And let me double check. Yep, 1,170 when I multiply those together. And what I'd be left with inside is a single y, an 8 minus y, and a dy. So obviously we need to do one little algebra step there. We need to distribute y times 8 and y times negative y. The integration then very simple. Add 1, divide by the new, add 1, divide by the new, and then we'll be integrating from 6 down to 0. Okay, so here comes the fundamental theorem. Let's see, I'm going to cancel 2 top and bottom, that'll just make that a little bit easier. So I'll have 4 times 6 squared, so that's a 144. I'll have 6 to the third divided by 3, so 6 to the third divided by 3 is a 72. 4 times 0 squared, and 0 to the third divided by 3. Okay, so obviously 144 minus 72 is 72. And when I multiply that by 1,170, I get 84,240 foot-pounds of work. Remember, we're in the U.S. system, so we have to unfortunately use the U.S. label for work, which is foot-pounds. Okay? Alrighty. So there's my second example. Oh, and I was going to shrink that down so you guys could see the whole thing. If anybody wants to or needs to, talk something over. Okay? And I am going to do a third example, but this video is getting kind of long, so I think I'll put it on a separate video. If you choose or would need to look at another example. Okay, so I'm going to pause this one, publish it, put it on Google Classroom, and then I'll have a third video that you can look at whenever you have the opportunity. Okay, hope you're having a good day, and we'll talk to you soon.